Hello and welcome back to our survey of plasma physics course. This is lecture 4, and today we're going to move to a new topic. And in fact, we still have one thing to say about the plasma parameter. If you remember, we've been talking about what the plasma parameter can tell us about the plasma itself. And I was somewhat conflicted whether to add this last thing to lecture 3, but I didn't want to make it overly long, even though this is going to take only a minute. So there is one more thing that the plasma parameter can tell us. And in fact, the expression we have in our textbook uses an expression for the electron collision frequency that I have not introduced. So I'll just state the result. And what the plasma parameter can tell us is how collective and discrete interactions relate to each other, as in which one is more important. And this may take a little bit more than what I'm going to say here, but essentially, let me put it this way, we can say that collective interactions, I'm going to put that in quotation marks for reasons that hopefully will be obvious in a moment. Over discrete interactions, same thing in quotation marks. Let's say the weight, the importance of these two, when I take the ratio, that ratio is large if the ratio between the two frequencies that we have encountered, the electron plasma frequency and the electron collision frequency with the ions, is large. I'll first put them down in words. Electron plasma frequency over electron ion collision frequency is large. So these two ratios go together, and from expressions that we have in our textbook, we can do a little bit of trivial algebra, which I'm not going to do. If you're offended by the lack of algebra in this course, just wait 5 minutes and you'll start being more happy. We'll do a lot more algebra in our next topic. Anyway, the ratio between these two quantities, frequencies, is, well, might as well use the equal sign. With the square root of pi over 2. Again, we did not derive the expression for the ion and electron collision frequencies. Actually, I didn't even write it down because it's kind of a messy expression, but I'm just going to take it from our textbook now. So this ratio is going to be 1 square root of pi over 2 times 128 plasma parameter divided by the log of 12 pi times the plasma parameter. It's pretty intuitive, right? Now, of course, if the plasma parameter is large, the log of the plasma parameter will go much more slowly than the plasma parameter itself, and therefore this ratio is going to be large. So once again, this can tell us that this expression shows that the plasma parameter can tell us something important about the plasma. In practice, if the plasma frequency electron plasma frequency is much larger than the collision frequency, then we see a lot of oscillations with the plasma frequency before we see a collision. On the other hand, if the opposite is true, that means that we see collisions before we can see even just a part of the period of the oscillation of the wave, so that the wave will not really have a chance to exist in the plasma. Okay, that is all we're going to say about this topic. There is one more section in our textbook about quantum effects, which I'm not going to cover. In short, I'm going to assume that quantum effects are not going to be that important for us. They're going to be something that we can ignore. And I'm going to move on to our next topic. Our next topic is going to actually keep us busy for a while. And I'm going to give it a generic name. We'll investigate this in some detail. What we're going to look at is the motion of essentially a single charge particle. What we could say, I could use the plural. In the presence of electric and magnetic field. Particle in the presence of fields. I don't need a full stop. Okay, so that is our topic, and you well, you may see some issue with what I'm doing here, or maybe not, because I haven't said enough to cause an issue yet. But let me be more precise about what I'm going to look at. What I want to consider is how a charged particle is going to move in a given electric and magnetic field. And this may appear reasonable. May not see any problem with it. However, if you think about it, what we'll do will tell us what's the motion of a single particle in a given electromagnetic field. But in a plasma, I'm going to have a lot of particles. And my discussion will apply to each one of them. Now, if I have particles moving, I'm going to have currents. But if I'm going to have currents, those currents are going to generate magnetic fields. And electric fields and magnetic fields will depend on the motion of, ultimately, on the motion of my charged particles in the plasma. If that's true, how can the fields be given? I'm not using a self-consistent model to understand what's happening. That is, in fact, the case, but we're going to start from the building blocks of our understanding of plasmas, and we're going to look only at the motion of a single particle, and let's assume that electric and magnetic fields are given, and there is only one particle. Well, then that's a pretty legitimate thing to do. And if there is only a single particle and there are strong electromagnetic fields, we don't have to worry about that particle modifying anything. So we should be okay. But always keep in mind, eventually we'll have to come back to a collective behavior of a plasma. The plasma itself is going to modify electromagnetic fields. And we will, in fact, see some hints of that pretty soon. Well, our main tool in this analysis is going to be the equation of motion for a charged particle in the presence of electromagnetic fields, and I'm going to assume that those are, again, given, and I'm going to be generic about whether I'm looking at ions or electrons. So I'm going to indicate a generic mass m, then the derivative of the velocity, mass times acceleration, is going to be equal to the forces in the system. Well, I'm going to have the Lorentz force, Q times E plus V cross B. And that's all I'm going to care about. You're familiar with this, of course. Of course, if the particle has a mass, we should put in gravity too. And there may be other forces. That's correct, again. But as you'll see, if you do a quick back of the envelope calculation, you should have the tools to do it pretty soon. The effects of a force like gravity are completely negligible with respect to the effects of electromagnetic fields for systems of practical interest. That should not be a huge surprise. We sort of know that the gravitational force is pretty weak compared to the other fundamental forces. Okay, now I've said multiple times my electric and magnetic field are given. They could be, in principle, anything. They don't have to be constant. They may be changing in time, and so on. That's going to be a pretty complicated problem. So what we're going to do is start from the beginning, something that you're already familiar with actually, and work our understanding and algebra out from there. First case, let me put that. I'll just call it a 1. We're going to look at the uniform and constant magnetic field. That is a magnetic field that does not change either in time or space, that does not depend on anything, and zero electric field. I prefer to call it constant. This is, of course, a case you're familiar with from physics 2. You know how this goes, but let me just write down a little bit of algebra. I suppose I can make this relatively quick. The first thing I'm going to do before I even solve for the motion is to show that the particle energy is constant. That should not be a surprise. How am I going to do it is I'll take v dot, where v dot is a time derivative of the velocity. I'm using the standard classical mechanics notation, times m times v, which is time derivative of the kinetic energy. So this is going to be equal to what I have on the left is the left-hand side of my equation of motion dotted with the velocity. So on the right, I'm going to put the same thing. I'm going to dot this with the velocity, v dot v cross b, which is obviously 0 because I have the cross product of v with another vector, and then I dot with v itself, but that cross product, as you very well know, is perpendicular to both v and b. So great, energy is conserved. And again, just in case, v dot indicates the time derivative of the velocity. Now, so that b is constant, doesn't depend on space, so I can just decide to set it up in any direction in my to arrange my axis, Cartesian axis, in a way that b is parallel to one of the axes. In particular, I'm going to pick my frame of reference so that b is in the z direction. I'm going to use the notation E sub z with a hat on the E to indicate unit vectors. Other books, including possibly our textbook, use different notations. It doesn't matter. You understand what I mean. Okay, then if B is in the Z direction, look back at my Lorentz force. There is no force in the Z direction because the force is perpendicular to B. Therefore, I need to solve the motion only for the X and Y component. There may be velocity in the Z component. If there is one, it's going to be constant because of the equation of motion in the Z direction. Let me write it. Sorry about that. gives us the following. QV cross B dot EZ, which is 0. So the first astounding result is that VZ is a constant. Now, not going to write the cross product and in detail. Let me move a little more quickly. This part, again, should be pretty familiar to you. And I'm going to consider it just a review of things you should already know. Okay, then what I get is that time derivative of Vx is going to be equal to the x component of the Lorentz force, which is going to be equal to Q times Vy times B. While the y component of the equation of motion, Vi dot, let me emphasize that there is a dot here, is going to be equal to, remember how the signs go for the cross product, minus Q Vx times B. And of course, I have to solve these two together. And of course, you know what we do. We take the time derivative of either one of the equations, let's say the first one, then Vx double dot is going to be equal to Q times B divided by M times Vy dot. But Vy dot is, I can get from here, it got the same expression, it's minus Q times B over M times Vx. So this gives me Q, the minus sign, QB over M squared times Vx. And this I'm just going to call omega squared. Vx, this is obviously circular motion with frequency omega. And I can pick my time, set time t equals 0 at an appropriate instant, so that I can write Vx simply as a cosine and Vy as a sine. So that's going to be V per cosine of omega t. And then I place this back in the equation for Vy. That was Vy is equal to over QB times Vx dot. I'm using the first equation solving for Vy, which gives me minus Q over Q V per sine of omega t. And these I can actually solve for the position. X is going to be equal to x naught plus V perp over omega sine of omega t, and y is equal to y naught plus Q over Q V perp over omega cosine of omega t. And before I move any further, I took this for granted, but let me remind you that where the absolute value comes from, I think it's obvious, and that's why I didn't dwell on it as I was writing my solution. When you take the square root of omega square, you take the absolute value. That's our convention. And of course, B is positive because I'm assigning the z-axis to be aligned with B. So the positive z-axis is in the direction of B. Mass is obviously positive, but the charge, as I said, we're working for both ions and electrons, could be positive or negative. Now, I'll let you play with it if you like, but so it should be pretty easy for you to be convinced of the fact that ions are going to rotate in the counterclockwise direction, and electrons are going to rotate in the clockwise direction, and they're both going to experience circular orbits. When I said ion, I meant positive ions. In principle, you could have a negative ion if we're looking at something different than, well, even in a plasma, it may occur at low temperature. But when I say ion, I always mean positive unless I specify otherwise. So, as I said, the motion is circular, and the center is R0, which has, oh, sorry, let me make this a little more clean. Coordinates x0 and y0. And the radius is what we call the Larmor radius, which is V per over omega. Now, I'll let you twist your hands and do the right hand contortion if you like, but I'm just going to state, and you should be able to verify that for both ions and electrons, I can calculate the current that goes through, say, the center of the circle, just to get a picture of what is happening. And that current, both ions and electrons are carrying a current because they're moving, so I can calculate the magnetic field that goes through the center of the circle, and that magnetic field is going to be in a direction that it's opposite to the direction of the original magnetic field. So the current carried by the plasma or by my charged particles is such that it reduces the original magnetic field, or in other words, this is a diamagnetic. Motion or effect, or current or material, or call it what you will. But diamagnetic is the keyword I'm interested in. Now, I did this wrong again. So sorry. You will remember that we said the fields are given, and the plasma is not going to change them. Well, Oh, finally. But I just said that the current carried by both ions and electrons is such that it will reduce the original magnetic field. That there is clearly a contradiction. But again, if I'm looking at a single electron, I'm not thinking of anything crazy, like a very weak field and relativistic motion of the electron. The current carried by a single electron is not going to modify the external magnetic field in any measurable way. So I can indeed safely ignore it. That was our case one. Let me see if I can pick the right pen on the first try now. Now let's make it a little bit more interesting and look at constant or uniform, or rather both, both constant and uniform B. But now the electric field is not zero. Okay. There are various ways to do this. This is not very complicated calculation, but if qualitatively, if I could write down my equation of motion and just look at my input, what are the electric field and the magnetic field, and ask the question, can I write this equation and find a solution for this V sub D? Okay, why would I want to do that? Well, if I can do that, then I will say that I want that velocity to be a constant, since both E and B are constant. If this equation has a solution, not surprisingly, the solution should be a constant. But if I can do that, then I will see that my total velocity for the particle is going to be given by this V sub D, which is going to be what is called the drift velocity, plus I'll call it V sub L, the Larmos gyration that we calculated before. Essentially, what I can do let me put that in writing. V sub L is the solution of the case where the electric field is zero. And in practice, what I can do is so do a transformation of coordinates that transforms the electric field away. Okay, well, let's see if we can if we can find a solution for this equation, or in any way. In order to do that, I'm going to use a simple trick. I'm going to take my first equation, the one that I wrote, E plus V drift cross B equals 0, and I'm going to cross it with B. So I'm going to write E cross B plus V drift cross B cross B, and this is still equal to 0. You all know how to use vectors. Remember the brackets. The order of the cross products matter. Now, E cross B is whatever it is. The second term in my equation, I can expand. And I hope you're familiar with this type of calculation. But this is the typical A cross B cross C type of vector combination that's going to give me A dot C times B minus B dot C times A. If you've never heard of this, try it. If you have no idea where this comes from, well, this is one of those things that we use so much that it kind of sticks to your memory. But if you want a handy place to look this up, I recommend getting the NRL formulary. Just do a search online, and it's a PDF. It's free to download. I keep it on my computer, and anytime I get confused with vectors, vector product and mixes and differential operators and curvilinear coordinates, that's where I look it up. Okay. Back to what I was saying. This is going to give me V drift dot B, where this B is this B. I got it from there. And this is going to be in the B direction, where that B is this B. And then I'm going to have minus B dot B, that gives me B squared times VD. Now, it may look like we have not really solved anything, but in fact we have, because V drift of B is 0. How do I know that? Well, let's go back to the original equation. E plus V drift cross B must be equal to 0. If V drift is in the B direction, the cross product with B is going to be 0, and therefore it's not going to be able to cancel out the electric field. So that there is no component of the drift velocity in the direction aligned with B that will matter for my equation. In truth, I could have an arbitrary velocity in the B direction, and that wouldn't matter. But that part of the velocity is going to be given by the complete solution of the equation of motion. So if this is the case, then I'll move to the next line. Then I know that E cross B minus B squared V drift is equal to 0, or V drift is equal to E cross B divided by B squared, which I always think is a pretty remarkable result. The reason why I say that is that this velocity does not depend on the charge of the particle. That is, it's true for both ions and electrons, and it's actually true for a single charged electron and an ion with more than one positive charge, but also does not depend on the mass of the particle. So this velocity is identical for any charged particle that's in my system. The only thing I need is a charge, and then the particle will move with this drift velocity. But now that I've found this velocity, I can write the complete solution for my velocity. That's going to be given by my V parallel, that was Vz in the notation I used earlier. And that's not going to be influenced by the magnetic field. That's the direction, the velocity parallel to the magnetic field. And then I'm going to put it to write V parallel with a vector sign, so it's clear that I'm including the direction there. The drift velocity, and then I'm going to have the gyration velocity. Of course, I'm here assuming that the electric field is not parallel to the magnetic field. If that was the case, well, E cross B is 0. But then I will have a straight acceleration of the particle in the z direction, because my particle would be free to keep accelerating in the direction parallel to the magnetic field, and the magnetic field will not make it turn, which is what is happening here. Notice that in addition to what I've already said, there is a little catch. That is, I've assumed that the particle does not move with relativistic speed. That's going to be the case for all we do in this course, essentially. If the drift velocity actually gets to be close to the speed of light, then things will become a little more complicated. But we're not going to worry about that case for now. Now, I would be happy if I knew how to make nice pictures and drawings. There is, of course, there's going to be one in our book, and you can find them anywhere. But maybe I can try to give a little bit of a physical intuition about what is happening with the drift. So let's consider a positive charge, an ion, and let's assume that the magnetic field goes down into the page, and the electric field points this way, up to the page. Then my ion is going to be moving in a circle. Let's see, a circle I can probably get from here. Something like this. And this is going to be the motion with E equals 0. But as my ion is moving, as it moves up the circle, it gets pushed farther and farther. So it's accelerating. In practice, the perpendicular velocity, velocity perpendicular to the magnetic field, is increasing, and therefore it's trying to, this velocity grow, it's trying to turn onto a bigger radius. But when it starts coming back down, then it's now moving against the electric field, so it's going to slow down and try to turn into a smaller circle. And then it gets to the turning point, it will start accelerating again and get into a bigger circle. And you see what I meant when I said I don't know how to draw. You'll find better pictures, but you will see that there is a net motion, in this case to the left. And if you check the expression that we wrote, you'll see that it's the correct direction. So that's the way it goes. Let's use this result for maybe one more thing. In fact, I like this result because it's telling us quite a bit about the possible motion of charged particles in electromagnetic fields. And here's what I mean by that. Let's assume that there is some other force that's not an electric force. It's not, there is no electric field is 0, but there is some other force. That could be, for instance, gravity. But it could be whatever. So in that case, my equation of motion is going to have on the right-hand side this force, generic force F, plus the piece of the Lorentz force that is relevant to our system. Now, since, of course, the charge is a constant, I can, just for the sake of it, write my equation of motion this way. Put a charge in front of everything, then divide by the charge, put the force in, and then I have the V cross B term. Well, do you see that this is the same equation I had before? I just say, well, my expression here, I'm just going to rename it and I'm going to call it E. And then I know what the solution of the equation of motion for this particle is. And in particular, the drift velocity is going to be E cross B divided by B squared, replacing the expression I have for E. This is going to be 1 over Q F cross B divided by B squared. That is, if there is some other force that is not due to the presence of an electric field, but to something else, I am still going to get a drift that is perpendicular, again, to both the force and the magnetic field. But in this case, it will depend on the charge. That is, ions and electrons will drift in the opposite direction. And that is about all we can do with constant fields, which I think is already quite a bit. Now let's move to after the customary division line here. Let's move to a more complicated case. Case 3, we're going to look at non-uniform magnetic field. And again, by non-uniform, I mean that the magnetic field is changing in space, but I'm still going to assume that it is constant in time. It does not change in time. Well, it turns out that this problem is quite a bit more complicated. So let me try again to give you a qualitative, intuitive picture. In this case, I'm going to try to do that first. And let's see how I do with my drawing. Okay, first thing, I'm going to assume again that the magnetic field is into the page or the screen. And now I'm going to assume that the gradient of B points this way, where by gradient of B, I mean the gradient of the magnitude of B, or the absolute value of B. So B is getting bigger as I move up in my screen page. Well, then let me start from a random point, for instance, here, and let's consider an ion, positive charge, and my charge is moving down. It will go in a circle, but the circle is actually getting bigger because the field is getting weaker. Let's go up a little bit. We have this expression for the Larmor radius, and we have this expression for omega. So if I didn't do it earlier, but we can do it now. Omega, 1 over omega is m over qb. So here I have m v perp. I'm going to assume that the radius is positive. So I'm going to use the absolute value. But the important thing is that the absolute value of the magnetic field is in the denominator. That means if B becomes smaller, the radius becomes bigger. And if B becomes bigger in the opposite way, the radius will become smaller. Then back to our little drawing here, B is becoming smaller, so the radius is becoming bigger. It is trying to make a bigger and bigger circle. Then it starts moving up, and the radius starts to become smaller because the magnetic field is stronger. So it will turn into a smaller radius, and then comes back down and does the same thing. So the radius becomes bigger, And what I end up is, again, a drift velocity that points, in this case, in the right direction. Now, if you try to do the same plot for electrons, let me emphasize which way this piece of modern art goes. This is the direction of the motion. Remember, ions gyrate counterclockwise with respect to a constant magnetic field. Now, if I have an electron instead, well, let me go back up here and emphasize that we're using this expression. That Larmor radius depends on the mass of the charged particle. That is, the Larmor radius of electrons is going to be a lot smaller than the Larmor radius of ions. I'm not going to draw it in the correct proportions. I wouldn't be able to if I tried, because it will essentially disappear. There is a big ratio between a mass of the ions and mass of the electron. But I'm going to do it in a different, redo the same picture in a different color. And for an electron, my magnetic field and gradient of the magnetic field go in the same way. I have a negative charge now that's coming down, gyrating in the clockwise direction, and the magnetic field is getting weaker, so this radius is getting bigger, and then it starts going up. The magnetic field gets stronger, so the radius gets smaller. Get up here, it turns around, the magnetic field gets weaker, the radius starts getting bigger again, and following, right. Sorry about that. This is going to go so badly. Here, I'll patch it. Following the motion of my electron in the correct direction, I can see what's happening. I have a drift velocity that points to the left, not to the right, which is quite different from what we saw in the E cross B case. Actually, I did not do the drawing for the E cross B case for the electron. Try to do it, and you will see that you get the same result. And the reason is that in that case, the force is in opposite direction for ions and electrons. They're gyrating in opposite directions, but the radius becomes bigger or smaller in opposite directions as well. And the sort of two minus signs, if you wish, will cancel each other. You end up with the same sign. Now, well, let's see if we can solve this problem. That's an easy question to answer now. This is actually not as easy as we would like. All the derivations you'll find in textbooks and so on are going to assume that the magnetic field is going to change in dimensions that are on scale length, I'm sorry, that are much bigger than the Larmor radius. Otherwise, it will be quite a bit of a nightmare to sort this out. Now, I am going to assume that the Larmor radius is much less than the absolute value of B over the absolute value of grad B. And if you just look at this for a fraction of a second, you'll see that what I have on the right, it also has a dimension of length, because on the denominator I have field over length. So the length comes to the top and the magnetic field cancels out. So this is a correct, a dimensionally correct inequality. But if I do that, that will allow me to approximate the magnetic field, or make a simple expression for the magnetic field. I'm going to do a Taylor expansion starting from some point, some initial or position of my particle, or the center of the gyration of the particle. Doesn't matter, because the two are pretty much the same. And then I have the first term in the gradient, sorry, in the Taylor expansion of the magnetic field, which is going to be given by R, where R is the changing position of the particle, dot grad B. Okay, now this is going to be a little bit of work, and it's not terrible, but it may be better to leave it be, leave you hanging, and we will see this in lecture 5.